In this lesson, I'm going to tell you about the laws of logarithms. Now, the logarithm laws can be found by converting the index laws into logarithms. But before we can talk about them properly, let's quickly review what a logarithm actually is. So this expression over here contains an index. We're assuming that a to the power of m is going to be equal to b. Now, one way to convert this into a logarithm is by taking the log base a of both sides. And then we realize that logarithms just cross out exponentials, so you're only left with the letter m on the left-hand side. So once we've done this, we can say that we can rewrite a to the power of m equals b as m equals the log a of b. But we also explained that there was a faster way than taking the log of both sides, which is this animation where you imagine the n pushing the a down and then the a ends up below the c. Now I'm going to need both of these, so I've just left them both here, as you're going to see pretty soon. But as we said in the lesson where I introduced logarithms, there are some immediate implications of this definition. For example, if we let m be the number 0, then a to the power of 0 always ends up being the number 1. So if we just repeat the exact same animation here, this will just tell us that the log base a of the number 1 is just going to be 0. So aside from this implication, if m is going to be equal to the number 1, then a to the power of 1 must be the same thing as a. And then, repeating the animation one more time, if this 1 comes down, then we know that the log base a of a is just going to end up being the number 1. Now, in a sense, these two rules are the simplest log rules. We know that the log base a of 1 is always 0, and the log base a of a is always 1, no matter what the choice of a is. However, from the index laws that we developed earlier, we can develop quite a few more log laws. So what we're saying here is that if we started off with some index laws, and we rewrote them as logarithms like we did up here, we can develop a few more logarithmic laws. So let's develop our first log law. We know that a to the power of m, all to the power of n, is the same thing as a to the power of m times n. Now we can actually take the log of both sides, or we can bring this a below the left-hand side. Now initially, this looks pretty complicated, but I want you to notice that a to the power of m is the same thing as b. So I'm going to get rid of a to the power of m and replace it for this b. So now we notice that the log base a of b to the power of n is the same thing as m times n. But we can make this a lot more useful if we realize that m is the exact same thing as the log base a of b. So I can replace the m for the log base a of b. So this gives us the first of our useful log laws. We can see that the log base a of b to the power of n is the same thing as n times the log base a of b. Another way you can think of this rule is that if we have powers inside of logs, we can pull them out in front. So as you can see, if we had an n here, it can come to the front. However, you do need to be a little bit careful with this rule, because if the n is actually outside the log, you cannot just bring it down like that. The n can only come down when they're inside the brackets that are applied to log. But rules are not so useful unless you see them applied. So let's bring out an example where you can see this used. Now, if you've already been watching all my videos on logs, you can probably already solve this problem without needing to actually use this rule. But we're going to use this rule so you can see it applied. We just want to know what the log base 10 of 1000 is going to be equal to. Now, the first thing I'm going to do is I'm going to rewrite 1000 as 10 to the power of 3, because after all, if you multiply 10 by itself 3 times, you get 1000. Now, this rule just tells us that we can bring this 3 down in front, so let's go ahead and do that as well. But then we know that the log base 10 of 10 is the same thing as the number 1, so we can replace this with 1. So the answer is just 3. So just to be clear, this log law over here is completely equivalent to this rule on the left. We just rewrote this to get to this. So we should look at the other index laws to get the other log laws. So for the next index law, we start with a to the power of m times a to the power of n is the same thing as a to the power of m plus n. Now I'm going to do the same thing, so I'm going to pull this a below the left-hand side to rewrite it as a logarithm. But at this point, we know that a to the power of m is the same thing as b, and also a to the power of n is the same thing as c, so we might as well write this as the log of a of b times c. So now we know that the log base a of b times c is the same thing as m plus n. But what is m and what is n? Well, we know that m is the same thing as log a of b, and n is the same thing as log a of c. So let's also replace them as well. So now we have our second log law. We know that the log a of b times c is the same thing as the log a of b plus the log a of c. So in other words, logarithms turn multiplication into addition. But again, I should show you this with an example. So if we want to find the log base 2 of 2 times root 2, then we should turn this multiplication of 2 and root 2 into addition. When we do this, we're going to end up with the log base 2 of 2 and the log base 2 of root 2 added together. Now we notice that the log base 2 of 2 is the same thing as 1, and then we can also replace this root 2 for a power of half. Now at this stage, we can also bring this half out in front of the log, so let's do that as well. So then, the log base 2 of 2 is just equal to 1, so it goes away, and then we just have 1 plus 1 half, which is 3 on 2. So therefore, the log base 2 of 2 root 2 is the same thing as 3 on 2. So from these two index laws, we were able to get these two log laws. But again, there is one more index law. Now, whilst it is possible to repeat the exact same process that we did for these two index laws on this index law, I want you to remember that this index law actually comes directly from the other two index laws. Now, as an exercise for you, you should try actually converting this into the final rule that I'm about to show you, remembering that a to the power of m is b and a to the power of n is c, and so on. But since this depends on these two, then the last log law can also depend on these two log laws, so I'm going to derive it directly from the log laws. So this time, rather than multiplying b and c together, I want you to imagine that we've divided b and c instead. Now, b divided by c can be rewritten as b times c reciprocal, so let me do that. But then, according to this rule, we can break up b times c reciprocal into log a of b plus log a of c reciprocal. And then finally, we'll use this rule up here to bring that n right down. In this case, n is minus 1, so we can bring this minus 1 in front, which converts this plus into a minus. So as we can see, this third log law turns division into subtraction. But I'll also give you an example to show you how it's used as well. So we want to find the log base 3 of 3 divided by root 3. Since we have a division here, we can turn this into the log base 3 of 3 minus the log base 3 of root 3. Now, just like last time, we know that the log base 3 of 3 is just going to be 1, and then this root 3 can be rewritten as 3 to the power of 1 half. Now again, this 1 half can come out in front, and then the log base 3 of 3 is just 1 again. So we just have 1 minus 1 half. Now 1 minus 1 half is of course the same thing as 1 half. Now at this point, you may fall into the idea that the log laws are just a bunch of rules that you need to memorize. But understanding them actually tells you a fair bit about how logarithms actually work. So let me show you another example to show you this. So this is a really chunky problem, so let's go through it together. The Richter scale is a special scale that measures the strength of an earthquake. To figure out the magnitude of an earthquake, which is the m, we use the formula m equals the log base 10 of the number a. Now a is really just how far the needle on a seismometer actually moves relative to a reference point. Now to understand what I mean by the needle on a seismometer, I'm going to go ahead and draw a seismometer to show you what I mean. So this thing over here is a nice simple seismometer. The way it works is that during an earthquake, the ground is going to start shaking, and this needle over here is going to move back and forth, tracing out something like this. Now, the harder the ground shakes, the further this needle is going to move left and right, and therefore the higher these spikes on the piece of paper on this rotating drum. So the question we're asking is, if on one day the seismometer moves X millimeters, and then on another day it moves 12 times as far as it did the previous day, how much will the Richter scale reading change? So we're going to explain this by saying M1 and A1 represent the first day, and M2 and A2 represent the second day. So if X is going to be the value of A1, then the value of A2 is going to be 12 times X, or in other words, A2 is just going to be the same thing as 12 times A1. Now this is something we can easily substitute into this bottom equation. Instead of A2, we can write this as 12 times A1. But now, at this stage, we can use this multiplication rule over here to rewrite this as the log base 10 of 12 plus the log base 10 of A1. Now at this stage, we know that the log base 10 of A1 is the same thing as M1, and we can use a calculator to figure out what the log base 10 of 12 is going to be. So as we can see, this means that M2 is equal to 1.079, which is the log base 10 of 12, plus M1. Now, initially this doesn't seem so important, but this should really show you how much variability there is in the strength of different earthquakes. Despite the fact that the ground is shaking 12 times as far, like really big shakes, the Richter scale only goes up by 1.079. So if we had an earthquake that had a Richter scale reading of 5, it would be barely perceptible to most people. However, if we had a Richter scale of 6, that would be 10 times as much shaking of the ground. And if we had a Richter scale of 7, that's actually a totally destructive earthquake. It can literally destroy buildings. So as you can see, logarithmic scales like this one are very important when you're going to talk about things that have a large range of numbers, like the Richter scale. However, when you do have a logarithmic unit like this one, you have to understand that small increases usually mean very large increases in the underlying numbers. So this just about completes the example I wanted to show. So I just have one more example to tell you about. So there is one more logarithm law that I think you should know about, but it doesn't really have a nice counterpart for the index laws. But what I'm going to do is I'm going to start off with some random index law, and then I'll show you how this rule works. So to get at this last log law, I'm going to start with the exact same expression that we started with before. But this time, I'm going to take the log base r of both sides, where r is just some random number that you can choose to be whatever you want. But then at this point, we can also bring the power of m down in front of the log law because of this rule that we found before. And then we can divide both sides by the log base r of a, so we can bring this whole thing to the bottom of this over here. But then, to finish this off, we also notice that m is once again the same thing as the log base a of b, so we can replace it over here. So we call this rule over here the change in base rule, because it allows you to change the base of a logarithm. Instead of writing the log base a of b, you can use the log base r of b, all divided by the log base r of a. This is useful in many algebraic problems, where you could simplify the problem by rewriting it with a different base. It's also very useful when you have a calculator that doesn't allow you to calculate the log of some custom base. But I can show you this with an example as well. So for this problem over here, I'd like to figure out what the value of len 16 divided by len 2 is. Now to do this, I'm going to need to use this change in base rule, where the base is of course e. So according to this rule over here, when we have a division of logs like this, with the same base, then we can rewrite this as the log base of a on b. In this case, a is 2 and b is 16, so we can rewrite this as the log base 2 of 16. And then to finish this off, we just have to ask, how many times can I divide the number 16 by the number 2 to get the number 1? And of course the answer there is going to be 4, because 16 divided by 2 is 8, divided by 2 is 4, divided by 2 is 2, and then divided by 2 is 1. And that took 1, 2, 3, 4 steps. So therefore, the len of 16 divided by the len of 2 is the same thing as the number 4. Now that just about completes all the examples I wanted to show you, so let's go ahead and summarize the lesson. In this lesson, we talked about the logarithmic laws. We said that if you knew that a to the power of m equals b and a to the power of n equals c, then you can rewrite them both as logarithms, and we use those logarithms to derive these laws. So the first law tells us that if we have powers inside of logarithms, we can bring them out in front. So the log base a of b to the power of n is the same thing as n times the log base a of b. The second law tells us that if we have a product inside of a logarithm, we can break it up into a sum. So the log base a of b times c is the same thing as log base a of b plus log base a of c. Then we also said that if you have a division inside, it turns into a subtraction. So the log base a of b divided by c is the same thing as the log base a of b minus the log base a of c. And then, the final rule we saw showed us that we can rewrite a logarithm in terms of any base that we like. So if we have the log base a of b, that's the same thing as the log base r of b divided by the log base r of a, where r is any number you like. Another thing to understand is that these expressions allow us to do more than just algebraically manipulate different expressions. They also give us a lot of insight into how logs actually work. Now, these log laws show up a heap of times during your studies of mathematics, so being familiar with them is definitely a very good idea, so you'll want to do some practice to get used to them. But at this point, this just about completes everything I wanted to say about the logarithmic laws. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.